A very good morning to our teachers. Today we are going to present with the title of vector field. Our group members have name is Kenjing. Then we have Chia Wei Yi, Tang Zheng Yi, and Yi Qi Wang. Okay, now let's go to Tang Zheng Yi.
Okay, so what is vector field? In vector calculus and physics, a vector field is an assignment of a vector to each point in a subset of space. For instance, a vector field in the plane can be visualized as a collection of arrows with a given magnitude and direction, each attached to a point in the plane. Vector fields are often used to model, for example, the speed and direction of a moving fluid throughout space, or the strength and direction of some force, such as the magnetic and gravitational force, as it changes from one point to another point. The elements of differential and integral calculus extend naturally to vector fields. When the vector fields represent force, the line integral of the vector field represents the work done by a force moving along a path. And under this interpretation, conservation of energy is exhibited as a special case of the fundamental theorem of calculus. Vector fields can usefully be thought as representing the velocity of a moving flow in space. And this physical intuition leads to notions such as the divergence, which represents the rate of change of volume of a flow, and curl, which represents the rotation of a flow. Next slide. Thank you. So in coordinates, a vector field on a domain in n-dimensional Euclidean space can be represented as a vector value function that associates an n tuples of real numbers to each point of the domains. This representation of a vector field depends on the coordinate system, and there is a well-defined transformation law in passing from one coordinate system to the others. Vector fields are often discussed on open subsets of Euclidean space, but also make sense on other subsets such as surface when they associate an arrow tangent to the surface at each point, a tangent vector. So more generally, vector fields are defined on differentiable manifolds, which are space that look like Euclidean space on small scales, but may have more complicated structure on larger scale. In this setting, a vector field gives a tangent vector at each point of the manifolds. That is a section of the tangent bundle to the manifold. So thank you.
Now I will explain the gradient vector field. The gradient of a function fxy in two dimensions is defined as nabla fxy equal to differentiation function in terms of xi plus differentiation f in terms of yj. The gradient of a function is a vector field is obtained by applying the vector operator nabla to the scalar function fxy. Such a vector field is called a gradient of conservative vector field. So now we have two examples for two dimensions. Next. So let's look into the example 1. So fxy equal to x squared minus fy power 3. So at here we only differentiate this function in terms of x for I, and differentiation function in terms of y. So we can get this. So for the second example, we do the same thing only. So next. So if the function is a scalar function of 3 variables, then its gradient vector field on 3 dimensional space is divided by nabla syz equal to differential function in terms of z for I plus differential function in terms of yj plus differential function in terms of zk. So we also have two examples here. We have two examples here also. Just apply the same formula, theory, so we can get the answer. Okay. That's all for me. Thank you.
Okay, and now I'm here to discuss the question of the gradient vector field, expand about the gradient vector field. Now here we are given a scalar function with 2 variables and a 2 given scalar function with 3 variables. Now we're going to scalar function with two variables. Next. Okay, for scalar function with two variables x and y, we have the equation of x squared y squared plus ln xy. To find the gradient function, we need to find the fx, where is the fx is the differentiation of x and fy is the differentiation of y. So fx, when we just differentiate the x and we get 2xy squared plus 1 over x. And when we differentiate y, to find fy, we get 2x squared y plus 1 over y. And we sub all the fx and fy into the equation, which is nabla fxy equal to differentiation of xi plus differentiation of y in terms of sy j. So we get the formula nabla fsy equal to 2x y squared plus 1 over xi plus 2x squared y plus 1 over yj, which is the gradient function. Next. And now this is the scalar function with three variables, which has x, y, and z. For three variables, we also do the same things, which has differentiation of x plus differentiation of y and differentiation of z. For fx, we will get the for fx, we differentiate the x and get the value yz exponent xy plus 4y cubed second square for x. And differential of y, we get xz exponent xy plus 3y squared tangent for x. And fz is equal to exponent xy. Then we sub all the value into the equation nabla f equal to fxi plus fyj plus fzk equal to this equation in vectors equation. That's all from me. Thank you.
Question B. First, we need to sketch the vector field for function fxy equals to 4yi plus x plus 2j. The rest will be 1, 1, 1, and 1, negative 1, negative 1, 0, negative 0, negative 1, 1, negative 1, and so on. So the vector by substituting x and y. After that, by using hand sketching graph, we will get this kind of graph. This kind of graph, we will take the coordinate between 0, 0 and 1, and we will get this kind of graph. And then by looking at this, sketching from this website www.geogebra.org and so on. By using this link, we can substituting f1 and f2. f1 we will substitute the value 4y, and for f2 we will substitute x plus 2, and finally we will get this kind of graph. And to prove that the hand sketching graph is similar, is correct, so we can comparing by using hand sketching graph and this website graph, and you can see the similarity here. And that's all for my part, and thank you.